Segment 2 of Chapter 10 Gas Laws. We left off with Boyle's Law. We haven't really started talking about it yet at all, but these are your gas laws. They always have the people's names after them, so it's Boyle's, Charles, Gay-Lussac, Avogadro. They all contributed to gas studies. And so for Boyle's Law, what Boyle did was study the relationship between pressure and volume. Work done at constant temperature as well as constant number of moles. So we're going to say, remember there's four properties: moles, temperature, volume, pressure. If we hold two of them constant and just look at the relationship between the two, then T1 equals T2. And what we see is as the volume decreases, the pressure has to increase. Pretty straightforward there. The next one we see is Charles' law. Now Charles, he worked on relationships of how volume would change with temperature. So holding pressure in moles constant, what happens when we start to mess with the temperature? Well, we're going to see that there is a relationship that is with temperature. As one goes up, the other also goes up. Now, the other key to this is that this is the Kelvin temperature. Kelvin. Right? And if you're not familiar with the Kelvin temperature, Kelvin is equal to 273 plus C. Okay. So did I get that right? So Kelvin is equal to 273 plus C. C is equal to Kelvin. Yes. So if we're at negative 273 degrees C, that would be 0 Kelvin. And that's actually considered absolute zero. So if Kelvin is 0, then C would be negative 273. So I had a little brain mishap there. Wasn't sure what's going on. But yeah, so Kelvin is equal to 273 plus C. All right, so the next one we see is Gay-Lussac's law. Gay-Lussac worked on the relationship between pressure and temperature. So now what we're going to do is hold volume and moles constant. And we're going to see that pressure also increases with temperature. And you might be familiar with this if you've gone out recent mornings here, went to go start up your car, and your tire lights are on. That's because the temperatures have been dropping, and so the pressure in our tires are dropping. And that will actually set off our pressure indicator in our car. This is why we don't heat canned foods on a campfire without opening them, right? So a can is under pressure, and if you throw a can of food into a fire, the pressure goes up, the can explodes. Okay? So he showed that the gas pressure is directly proportional to the absolute temperature. So again, whenever we're dealing with temperature and gas laws, it's always safe to be in Kelvin. You have to be in Kelvin for Boyle's, Charles, Gay-Lussac's. You don't have to be in Kelvin necessarily when you're doing other calculations. However, Kelvin will always work. Celsius does not. So a lot of times whenever you're doing your calculations, make sure you're in Kelvin, and then you can always convert over to Celsius when you're ready. All right, so we know that pressure then would be proportional to temperature, and so as pressure goes up, temperature goes up. At high temperature, we automatically have high pressure. At low temperature, we have low pressure. Now what we can do is take these three gas laws and turn them into the combined gas law. So the ratio then would be the pressure, the volume, and the temperature all together. So PV over T. And of course, we can then look at scenarios where we do something to the gas and see how it changes. Now, this ratio is going to be constant for a fixed amount of gas. So as long as we have the same number of moles, then it's going to be a fixed constant, right? So PV over T would equal a constant for a fixed number of moles, which means we could say P1V1 over T1 is equal to P2V2 over T2. Or another way that I like to write it is just go ahead and take that cross multiplication away from you and say P1V1 T2 is equal to P2V2 T1. Right? So all I did was cross multiply those T's for you, and that's just an easier way to remember it. Not so much in 150, but in lower levels of chem when we do gas laws, quite honestly, I'll see the answer that's inverse quite often where they forgot to put T2 in the bottom or put T1 in the bottom, whichever it may be, and then they answer the question and give me the inverse answer because they forgot that the T was actually in the denominator. Again, not as often with 150. You all pretty much know your way around math at this point. All right, so we have the combined gas law then. And then again, all T's have to be in Kelvin. The value of pressure and volume can be any units as long as they are the same on both sides. So typical math. Only equation you really need to remember is this one. The rest all fall out of this one. So if you say you have constant temperature, then you can see you have Boyle's law. If you have a constant pressure, then you have Charles' law where you have V1 over T1. And then finally, if you hold the volume constant, then you get P1 over T1, which is Gay-Lussac's law. So it gives all the relationships needed for the fixed amount of gas under the two sets of conditions. Now, how other laws fit into the combined gas law, we just did this. Boyle's law, T's are equal to each other. Charles' law, P is equal to each other. Gay-Lussac, V is equal to each other. And then, of course, those drop out of our equation. All right, so we can use this to calculate the effects of changing conditions. Can't emphasize enough, your temperature has to be in Kelvin. Then the P and the V in any units as long as they cancel out. So here, if a sample of air occupies 500 milliliters at 273.15 Kelvin in 1 atmosphere, what is the volume at 85 degrees C and 560 torr? So again, we can plug and chug this. We know we're starting this at 760 torr because we're at 1 atmosphere. We'll multiply that by the 500 milliliters. Then we'll divide that by our 273.15. Right? So that was going to be T1, P1, and V1. And then we have a T2, we have a P2, and we're going to be looking for V2. So 560 torr goes in. The 358, remember we have to be in Kelvin, and they gave us degree C here. So we'll simply add 273 to that, and that gives us the 358. Now we can see the torr will cancel out, the Kelvin will cancel out, and we'll be left with milliliters. And so the answer here is 890 milliliters. All right, what will be the final pressure of a sample of nitrogen gas with a volume of 950 meters cubed at 745 torr and 25 degrees C if it is heated to 60 degrees C and given a final volume of 1,150 meters cubed? All right. First, the number of moles is constant even though the actual number is not given. So we can just let it be 1. It doesn't matter. It's the same in both. That's all that's going to matter for us. You are given volume, pressure, and temperature for the initial state of the system as well as the temperature and volume for the final state of the system, and you must find P final. This is a clear case to use the combined gas law. So list what you know and what you don't know. Convert all your temperatures to Kelvin, then solve for the unknown. So we'll list everything off. We know P1 is 745 torr. V1 we were told 950 meters cubed. T1 will convert. We were told it's 25 degrees C, so we'll make that 298.15 K. P2 is what we're looking for. V2 we're told was 1150 meters cubed. T2 they told us 60 degrees C, and so we're going to add 273 to that to get 333.15. P2 then would simply equal P1 V1 T2 over T1 V2. At this point we plug and chug. We didn't worry about converting those meters because they're going to cancel each other out in the equation. Kelvin will cancel out. We'll be left with a pressure and torr, and after we run that through our calculator we get 688. All right, let's try another one. Anesthetic gas is normally given to a patient when the room temperature is 20 degrees C and the patient's body temperature is 37 degrees C. What would this temperature change do to 1.6 liters of gas if the pressure and mass stay the same? So what do you know? Pressure and moles are constant. So combined gas law simplifies to Charles' law. Right? So pressure and mass, i.e. moles, stay the same. And so we're left with Charles' law. Go through the same process. We know we have 1.6 liters. We know it's at 293 K. We want to know what the new volume is at the 310. So list what you know and what you don't know. Convert all your temperatures to Kelvin. And now we'll plug and chug for V2. So 1.6 times the 310 divided by the 293. And we get 1.69 liters. Hopefully you're going through these pretty quickly as well. You're not getting stuck on any of these. A lot of maybe just rehashing what you've seen in the past, and hopefully there's nothing new here. If you have questions or it is new to you, obviously you can go through it a couple of times by just, rewinding or whatever and watching the video again. But if you're really getting stuck, don't hesitate to get a hold of me. You can reach me on Zoom, so send me an email. We'll set up a Zoom time. We're done our labs, so that'll be the easiest and best way to get a hold of me and get help. So don't hesitate to do that. You can come to an office hour, student hours, or again, make an appointment. So, which units must be used in all gas law calculations? Kelvin for temperature, atmospheres for pressure, liters for volume, or no specific units as long as they all cancel. And again, I can't emphasize this enough. Kelvin, 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 right? Make sure you're in Kelvin whenever you're doing the calculations. All right, in order for the combined gas law to be used, what variable must be the same under both sets of conditions? And hopefully you picked E, the amount of moles. All right, so pressure and volume and temperature can all change, which means all three of them can change, but moles for the combined gas law to work has to be the same. All right, so relationships between gas volumes. In reactions in which products and reactants are gases, if temperature and pressure are constant, then we know there's going to be a simple relationship amongst the volumes. So here we have 1 H2 plus 1 Cl2, and it's going to make 2 HCl. Well, think of it this way. If temperature and pressure remain constant, then volume and moles have to have a relationship. So if I have 1 volume of hydrogen, 1 volume of chlorine, that's going to give me 2 volumes of HCl. If I have 2 moles of hydrogen, 1 mole of oxygen, and 2 moles of water, then I know hydrogen plus the oxygen will have to equal the water. So we'll have 2 volumes, 1 volume will equal 2 volumes. Ratios of simple whole numbers. Okay, so it's all about the coefficients. Avogadro's principle, when measured at same temperature and pressure, equal volumes of gas contain equal number of moles. So again, it's not going to matter what the gases are. If the temperature, pressure, and volume are the same, then the moles have to be the same. The volume of a gas is directly proportional to its number of moles, and we represent moles with the letter N. So V then has to be proportional to N at constant pressure and temperature. So the coefficients then have to work out. If we have 1 and 1 and 2, that means we have 1 volume, 2 volume, 1 molecule, 2 molecule, 1 mole, 2 mole. Okay, it has to work. If 3 volumes of hydrogen are reacted with 1 volume of N2, how many volumes of ammonia are produced? Hint, write the chemical reaction. Okay, so if you write out the chemical reaction, then you get 3 hydrogens plus 1 nitrogen produces how many ammonia, NH3? And hopefully you've got 2, right? And if you want, there it is, and you can go back and balance it. All right, so standard molar volume then. So now we're looking at how volume and temperature and now moles are going to come in. So now we care about moles. We're going to look at molar volume. The volume of 1 mole of gas must be identical for all gases at the same pressure and temperature. So we can set up what we call standard temperature and pressure, STP. At STP, the gas has to be at 1 atmosphere and 273.15 Kelvin. Under these conditions, 1 mole of gas will equal 22.4 liters. Right? So we can use that as a conversion factor because it's an equality. 1 mole, and it doesn't matter what the gas is, 1 mole is equal to 22.4 liters. 22.4 liters then is our standard molar volume. So as long as we're at standard temperature and pressure, that will hold true for any gas. Calculate the volume of ammonia formed by the reaction of 25 liters of hydrogen with excess ammonia. Or excuse me, nitrogen. We're making ammonia. So we have N2 plus 3H2 produces 2NH3. We've got 25 liters of hydrogen. We have as much as much nitrogen as we need. How much ammonia will we make? So we have 25 liters of hydrogen times 2 units of ammonia for every 3 units of hydrogen. Based on the coefficients, that gives us 17 liters. Liters of hydrogen will cancel out, and we're left with liters of ammonia. All right, same equation, same reaction. If 125 liters of hydrogen react with 50 liters of nitrogen, what volume of ammonia can be expected? So first, we'll figure out the hydrogen, right? This is a limiting reagent problem. Look at that. They sneak right in on you. Liters of hydrogen cancel out, and we've got 83.3 liters of ammonia. Now that's based on the hydrogen. Now we'll do the nitrogen. For the nitrogen, it's 2 to 1. Liters of nitrogen cancel out, and it says we produce 100 liters of ammonia. Again, limiting reagent suggests then that we can only make 83.3 liters, and we will have excess nitrogen. All right. How many liters of nitrogen at 1 atmosphere and 25 degrees C are produced by the decomposition of 150 grams of sodium azide? And then I give you the reaction here, right? So you have 2 sodium azides will produce 2 sodiums and 3 nitrogen gases. All right. So you're going to take 150 grams of the sodium azide, convert that to moles. Looks familiar, doesn't it? Then we're going to use our balanced chemical reaction to figure out moles of the nitrogen. Now we've solved for moles of nitrogen. We want to know how many liters at 1 atmosphere and 25 degrees C. So everything cancels out. We're now in moles of nitrogen, 3.46, and remember, 22.4 liters per mole. So we're going to take that 3.461 moles, multiply by the 22.4 liters, moles will cancel out, and we're at 77.5 liters as our answer. All right. Now we know how much, right? This is how many liters at this are produced by the decomposition of 150 grams of the azide. So we have V1 over T1 is equal to V2 over T2. V2 is equal to V1 T2 over T1. So we get 77.5 liters times the 298.15 Kelvin divided by T1 is 273.15. That's going to give us 84.6 liters. Now, why did we do the second step? Well, remember, first we calculated at STP, but what is STP? Standard temperature and pressure is 1 atmosphere and 0 degrees C. This question said 25 degrees C, so we had to do a Charles law to adjust for that temperature. All right, kelvins will cancel out, and you're left with the 84.6. So now you've seen some tricks. Let's try one. How many liters of SO3 will be produced when 25 liters of sulfur dioxide reacts with 75 liters of oxygen? All of your gases are going to be at STP for this question. So how many liters of SO3 will be produced when 25 liters of sulfur dioxide reacts with 75 liters of oxygen? Hopefully you came up with 25. If not, let's take a look at what you should have done. 25 liters of SO2 times 2 liters of SO3 over 2 liters of SO2 would give you 25 liters of SO3. 75 liters of O2 times 2 liters to SO3. Remember, this is based on the chemical reaction, so hopefully you wrote that out. They did not do that for us. So here what they did was they took SO2 plus O2 produced SO3. Then to balance it, we need a 2 here, and we need a 2 there. Okay, so that was the chemical reaction. These are your coefficients. And of course, for the second one, we come out to 150 liters. And we know that that means once we make 25, we run out of SO2, so the reaction will stop at that point. All right, so dinitrogen pentoxide decomposes into oxygen gas and nitrogen dioxide. If all the gases are at the same pressure, temperature, what volume of gas is produced when 13 liters of dinitrogen pentoxide was completely decomposed? So again, the first thing you need is the chemical reaction. So you have 2N2O5 goes to 4NO2 plus O2. So 5 liters of gas are produced for every 2 liters of N2O5 that decompose. Now, how did we get that? How do we know it's 5 liters of gas? Well, here, remember, we're going to sum up the sides. So we have 2 units on the one side producing 4 and 1. That's where we get the 5 from, right? So for every 2 units here, we're going to produce 4 units of this guy, 1 unit of that guy. That means this side means we're going to have 5 units altogether. So then we're going to start with our 13 liters of the dinitrogen pentoxide. We know we're going to make 5 liters of gas for every 2 liters of the dinitrogen pentoxide. That's how we get the 32.5. Liters of N2O5 cancel out. All right, so that's it for our combined gas laws. The next thing we're going to do is develop the ideal gas law. So we'll stop this segment here, and we'll pick up with PIV-NERT. So talk to you soon.